So this is a bit of a personal talk for me, but I will do my best to also make it relevant to the conference. So before I start, show of hands, how many have heard about buffer bloat before? Awesome. Okay, so how many have know who Dave Täht is? A couple of people. Okay, great. How many has met him? Couple of people. Okay, so this is Dave. He was a co-founder of the Buffer Bloat project and the self-appointed nagger-in-chief. He would travel around the world and talk about buffer bloat to people who needed to hear it, whether they wanted to or not. And he passed away on April 1st this year. So I was originally going to give a different talk here, but after this happened, I wrote to the organizers and asked if this would be an appropriate thing to do here as a way to honor him and his work. And so the idea of this talk is I'll talk a little bit about Dave himself and my relationship with him, and then I will give sort of a whirlwind tour of everything buffer bloat in the community and Linux. And it's sort of meant to be an overview, and then I will try to draw talk a little bit about some of Dave's principles that we can all apply in our work going forward as sort of a way of honoring him and his life's work. He's done a lot for all of us. So apart from being the Buffer Bloat project co-founder, he was also a huge space nerd, all-around dreamer, musician, songwriter. His personal sort of motivation for going and working on latency for all of us he wanted to play music across the internet. So he wanted latency to be low enough that you can, across town through your internet connection, have a jam session with other musicians. And for those of you who are into music, you know that this has some pretty stringent latency requirements. So you sort of have to match the speed of sound across a stage to be able to do this. And that's like a stage this size. It's around like 30 to 50 milliseconds, which is the absolute maximum reliable delay you have to be able to synchronize and play music together. So that was sort of his grand vision, which I'm not sure we have achieved yet, but we've come a long way. So, and Dave was relentlessly working on this, selflessly turned down many high-paying jobs because he wanted everything he did to be open and available to everyone, be part of the community. And here he is in the LibreQOS, which is one of the projects he's been part of here, booth at a conference, I forget where it is. With his customary guitar that he brought everywhere. He was also writing GPL-themed folk music, which you can look up. He has a song that's called "It GPLs Me," which I'm not going to play it, but you can look it up on YouTube and find it. So I first met Dave in this charming place just across the bridge in Bella Center in Copenhagen, where he was at that was the combined Ubuntu Summit / Linaro something in 2012, and he wrote out on the Buffer Bloat mailing list he will be there, and I asked, can I come say hi? And this is what he wrote, very sort of typical of him. Come on down. He just wants to write a spec for the Buffer Bloat test and get some awareness. And the food was good and free. It's very sort of typical, come on down, everyone is welcome, let's all collaborate on this thing. And so we did, and this is, as I said, in 2012, so in the just over almost a decade and a half since I've been collaborating with him. This is us showing off our testbed at my university in Karlstad, where he came and visited. I wrote my PhD on buffer bloat and everything around it, and Dave, I would not have finished that without him. He was instrumental in both getting me interested in this and helping me along as just a random university student figuring out what to do for their next project, and he would help me set things up and get through it. So he's an amazing guy. done so much for the community. And I will try to give a bit of an overview of both the history of buffer bloat itself and what have been the community efforts to deal with this, and then I have an overview of some of the innovations that have gone into the Linux kernel specifically to fix this on the networking side. So hopefully this will also, I don't have time to go, this is like, as I said, a decade plus work, so I don't have time to go into a huge amount of detail on each thing, but I will try to give you an overview of what's been going on and what is happening. And if you are interested, you can go look it up, or you can come ask me afterwards, and I'm happy to talk at length about any of it. So this is buffer bloat, this graph here. This is a test that runs about a minute, and after in the first 5 seconds, you can see the ping is fine. And then what happens here after 5 seconds is that a bulk connection starts up, and the queues in the bottleneck of this networking link starts to fill. And then suddenly, you get 800 milliseconds of latency on your connection. So this is like the original thing where you have a big FIFO queue, and as soon as you start filling up the link, you will get all this queuing. And we've basically fixed this in Linux. There's algorithms now. I will go through the different ones. I don't have all the nice graphs of what it looks like now. I'll just go through some of the mechanisms and history of what we've done. But right now, this if you set up your Linux system, even with the defaults now, this will be basically flat for the same test. So it all started in 2011. ACMQ. This is Jim Geddes and Kathleen Nichols, who is one of the authors of the cuddle algorithm. They wrote this article calling out, I think this is where they coined the term buffer bloat. And as you can see, today's networks are suffering from unnecessary latency and poor system performance. This was sort of the initial call out of this is going on, we need to do something about it. And it's not like congestion has not been known before that, but the fact that this was so endemic in every connection you had, every home router, every system basically, every bottleneck on the internet had this problem. And this was the article calling out, describing the problem, and naming it as buffer bloat. So this started the whole effort, and as I said, I got into this about a year later in 2012 when I was a master's student and looking for something to do for my thesis. And I came across Jim, he was at Bell Labs at the time. He's also one of the original authors of the X11 protocol and did a lot of stuff. He also had a blog post, and he's the other co-founder of the buffer bloat effort. And Dave came into this shortly after. So one of the projects that was started to sort of try to do something better with this was the Serword project, which it was a soft fork of OpenWRT at the time, which was trying to collect a lot of the fixes for buffer bloat. You can see a lot of the, you can see the feature list here. This is sort of the archived site. It's all been merged into OpenWRT itself now, so the Serword project doesn't exist, but this was one of the, you can see the dates here, 2013. This started up as sort of the experimental platform. And we have this, if any of you are familiar with the WNDR 3800, this little home router, Netgear device from 2000 something, which had a tiny MIPS core and an Eth9K Wi-Fi driver, and it still works great. If you don't need hundreds of megabits of bandwidth, this is still a great Wi-Fi router for just the consistent low latency that you get out of it. I still run several of them. It still works. Another project that we started out on this was the Make Wi-Fi Fast project, where we tried to get some of these fixes for buffer bloat into the Linux Wi-Fi stack, which of course had the same problem. It was everywhere, and Wi-Fi has some specific problems because it's a shared medium. So over the course of a connection, your bandwidth will vary by an order of magnitude depending on who happens to share the airwaves with you at any particular time. So this was a project also started up in the buffer bloat community to try to get fixes into the Linux Wi-Fi stack. Then the IETF also got in on the action. There was an HUM working group which was chartered to define new queue management algorithms. So that is really the main innovation that came out of this whole buffer bloat effort was queue management. So some of you may have heard of RED, random early detection, which is way older. And it's one of these features that you have on your Cisco router and no one turns on because it's really hard to configure, and if you do it wrong, nothing works. So one of the innovations that came out of this working group was several new queue management algorithms that are no knob. You just turn them on and they improve things by an order of magnitude. And this was the HUM working group was chartered to do this. I don't have a date on this slide, but I think it was 13 or 14 that it started. Yes, and then LibreQOS is one of the more recent projects that Dave was involved in the last couple of years. So this is a piece of software that uses the Linux networking stack as a buffer bloat mitigation mechanism using one of Jesper's innovations, the XDP traffic steering. So it's software you install on a middle box, and you can have traffic shaping for all the customers on the network, and it will ensure fairness and low latency, no buffer bloat. And the XDP thing is used to steer traffic, so it scales across CPUs, and you can push, I think they say they're up to 80 gigabits on a single off-the-shelf server of pushing traffic through this and making sure that the network doesn't suffer from this. So all of these projects, all of these innovations and things that happened built a lot on things that happen in Linux because, as we all know, Linux is everywhere, and a lot of the places where this happens, there's a Linux router that is the bottleneck. So buffer bloat happens less in core networks where you have the big iron Cisco switches because ISPs wildly over-provision their networks to avoid congestion, and if you don't have congestion, you don't have buffering, and it's all just immediately forwarding packets. But everywhere you get a bottleneck, which you get in any network, no matter if you're going at 1 megabit or 100 gigabits, somewhere will be the part of the network connection that is the slowest, and that's why you get a bottleneck. And a lot of this happens in home routers, Wi-Fi access points, end-user devices, all these places, which mostly run Linux. And so also Linux happens to be open source and available, so you can innovate in it without getting vendors to pay attention to you. For example, if you just happen to be a student who's interested in this, you can go and hack on the code. And this is, like, in my mind, one of the amazing things about Linux, and one of the reasons I'm still in this space is to be able to work on this. But you all know that. So one of the first innovations that came out of the AQM working group and was pioneered in Linux is the Cuddle AQM, and later Pi came out of Cisco, but is also in Linux now, and their FQ variant. So these graphs are from the original paper describing the Cuddle algorithm, and you can almost see the link to the paper down there. So this is the sort of a pipe of a TCP connection, right, where the green things are packets, and there's a bottleneck where the link gets slower, so the packets get squeezed out, and then they start having a distance between them, and this is the queue you get. And then you get the steady state of TCP after one RTT. You get this ACK clocking back, where the ACKs come at the rate that the packets arrive after the bottleneck. And before that, you will get a spike. So this is what happens with the queue length over time. And the the main insight of the Cuttle algorithm is that this spike is grid buffering, because you need to be able to ramp up your TCP connection to fill the pipe. But this one over here, you don't want a standing queue. You don't want the queue to persist. So you need to be able to deal with transitory spikes in queuing latency without incurring a standing queue afterwards, after the slow start of TCP. And this was, no one knew how to do this at the time, because you could fiddle with parameters of red and do random detection and so on and so forth, and you had to know the bandwidth and so on. And so the main insight, which is one of these things that seem obvious in hindsight, is that instead of trying to tune algorithms from the bandwidth and parameters and all this stuff, we can just, when you have a queue here, when a packet enters the queue, you just timestamp it. And then it sits in the queue for a while, and you send it out. And then you read the timestamp, and you compute the delta between in-queue time and D-queue time, and this gives you the queuing latency. Obvious, right? But no one was doing this at the time. And the nice thing about this is that it's completely invariant to the bandwidth. You can just directly measure the queuing size, so you don't need to tune anything. You can just say, well, time is what I'm interested in. I don't want more than 5 milliseconds of queuing. And if I have that, I need to do something about it. And what you do with an AQM is you start dropping packets to tell TCP to slow down. And so the second innovation was we don't want to do that here, because then we will not get the spike that we need to fill the buffer. We need to wait a little bit. So what Cuttle does, basically, it looks at the queuing time of packets as they're dequeued, and if it goes over 5 milliseconds, it sets a flag that says, I'm over the time, and then it waits 100 milliseconds, which is roughly not so much anymore, but at the time that was like a reasonable, maybe a bit pessimistic round-trip time for a connection across the internet. These days, CDNs are a lot more common, so you will get tens of milliseconds, but it's still, but there's an auto-tuning, so it still works reasonably well. So you wait for a little bit, and if the time is still if the queue time is still above the threshold that you have of 5 milliseconds, you start signaling. And this means that regardless of what your bandwidth is, and regardless of whether or not the bandwidth is the same as it was 5 seconds ago, you can still react in a timely manner, and you can still signal TCP to slow down. And so this works really well, and this will get you down to 30 or 40 of milliseconds. And then the second innovation was this FQ bit, where you do per flow queuing, and there's a short flow optimization. I'm not going to go into in detail, but basically it gives you, it's a priority queue for small flows. So your DNS traffic or your ACKs or your SYN packets will get automatic priority for the start of the connection, which means everything is a lot snappier. And the latter became RFC 8290, which Dave got on number plates. I have one of them after he pulled. I assume after he pulled it off the Caragon, he gifted me one, and I still have that home. Just to this is the main innovation. Just now the default in Linux FQ-Cuttle will be, if you go TCQ-Disk on most distros, you will have FQ-Cuttle on your devices by default. Second thing that happened in Linux was, okay, so you have the QDisk layer, you're controlling your queues, everything is great, but then you have a NIC that you're sending packets to, and these NICs also have queues, and they can be quite large, especially on NICs that try to go at 10 and 100 gigabits. You will have transmission rings of 4,000, 8,000 packets, and this can be a significant contributor to latency in itself, and it's after the QDisk layer. So if your NIC is your bottleneck, you are not actually controlling the queue with all these smart algorithms that we put into the QDisk layer. So BQL is byte queue limits. These are the which is Tom Herbert of who's also a kernel developer, came up with this, and this is a Medium post that he did sort of 10 years later, explaining it and having some graphs. So what it will do, it will say, okay, we're sending data we ran out of bytes to send, so we need more queuing. Or it will go, we were sending data and we still have some slack, we still have too much data queued. So we'll sort of tune how much data it puts into the hardware queues measured in bytes and try to keep the hardware busy, but queue no more than what is needed for this. And this means that you move the bottleneck up to the queue disk layer where you control it. And this was also central to managing buffer bloat in Linux machines. So those two together give us excellent latency on Ethernet links. Then we have Wi-Fi, where we did this. This was part of my work during my PhD, where we do on Wi-Fi today, we will completely bypass the queue disk layer. And we put FQCoddle basically into the Wi-Fi stack. And the reason we needed to do this instead of having it in the queue disk layer is that on an access point, you have one network device that will send out to different clients, different stations, and each of these stations can have different signal quality, and that means it will have, because of Wi-Fi does automatic rate control, tries to figure out how good is my signal, what is the highest rate I can send off. Lower rates gives you longer propagation because it encodes traffic differently, encodes data differently with more sort of, it can be more noisy and still get through, but it will be slower. That's basically what rate control does in Wi-Fi. And that means the same link can get different packets that go to different destinations with order of magnitude difference in latency. So you need to, so that in order to ensure that different stations don't interfere with each other. So you don't have one slow station that will affect everyone else. You sort of need to do round robin scheduling, like we had with the schedulers before. You need to do round-robin scheduling between stations, and for each station, you then need a smart queuing algorithm for FQCoddle, and you need to deal with retries, and this is sort of the architecture we came up with. And this is now, at the time, this was the Ath9K driver, hence the Netgear router that we implemented this on first, because that has the nice property of having almost no firmware, so it's all done in software. And since this has been ported, so now every driver in the Linux stack will use this, and there's some additional AQL is airtime queue limits, like byte queue limits, which tries to keep data out of the firmware, and so on and so forth. So we basically did the same sort of thing for Wi-Fi, but with its weird characteristics. Then we have TCP small queues and packet pacing, which is another thing that went into Linux. This is more going back to the endpoint, trying to keep your TCP connection on your device from filling up the buffers inside that device itself. So you have TCP up here, which will send some data down to the NIC through the queuing layer and all this. And there's a socket buffer. So when your application sent data to the kernel, there's a socket buffer that you can fill up with data, and that gives you another layer of queuing, which can also affect your latency. So once you've queued something to the socket buffer, you cannot send new data. So if you have different things that are going over the same TCP connection, you will have to wait. So what TCP small queues does is that it adds this completion signal via the fkbuf destructor function. So all the way down in the driver, when the NIC has sent, when the packets have gone to the NIC, the completion interrupt comes back to the driver, which will say, okay, I can now free the memory, and the destructor will be called, and that will signal all the way up to the TCP stack that now the packets have actually been sent. So this whole pipe can be as small as possible. And then again, TSQ, TCP small queues, measures things in milliseconds, so it tries to keep only a handful of milliseconds of data queued in the whole stack, which means that you can avoid a lot of the bloated queues throughout the whole networking stack for local TCP connections. Another thing is pacing, where the TCP stack knows the round trip time of the connection, and that means it can sort of predict it also knows the bandwidth because of congestion control. So it's sort of the round trip time and the bandwidth gives you inter-packet gap that is needed to keep packets flowing smoothly. And there's a whole pacing engine that goes all the way down to, you can actually get it into hardware these days, but at least all the way to the queuing layer where the TCP stack can set timestamps on each packet so they flow smoothly and don't build up a queue in bottlenecks. So this is like packets that are nicely paced out instead of being bursty. That was another thing that is now in Linux and turned on by default and will help you. Then we have BBR. This is the paper by Neil Cardwell and some other authors that could not fit on the slide, which is the congestion control algorithm that came out of Google. And the first version of BBR is upstream in Linux as TCP BBR, and you can turn it on, and it will do things a lot differently. So what it does is it builds a model, it measures the bottleneck and tries to fill it. Instead of just doing packet drop like Cubic. And there's now BBRv2 and a BBRv3, which have not been upstreamed yet. So if you know someone from Google, go and poke them to get it upstream, because BBRv1 then turned out didn't work in all cases and so on. So this is an active area of research, also congestion control. It has been for 40 years. But there's been some innovation here which will help you from the sender side try to avoid bottlenecks. Yes? Yes, I think it's actually bottleneck bandwidth and round trip time, but I may be mistaken. Yeah. Then there's cake. So we have pie. There's also cake, and this is a QDisk that you can install, which takes a lot of the. We have these scripts that set up queue management for your home gateway, and we turn it into a QDisk that is single purpose for this. So it gets you per host fairness, it gets you diff serve priorities, it gets you ACK thinning. There's a lot of sort of an integrated bandwidth shaper that you can put on your home gateway, and it will shape traffic to 95% of your bottleneck. So if your bottleneck is bloated, you can make sure you don't fill it by shaping your traffic to just under the bottleneck and all this stuff. And this is a QDisk that we wrote up this paper describing it, and it's in Linux. I'm the maintainer, and there's ongoing work to sort of try to make it scale across CPUs and so on and so forth. But this is a sort of one time you just do TC QDisk cake bandwidth something something, and it just turns on and it just works. Is the idea. Yes, so that was sort of a whirlwind tour of buffer bloat in Linux, and I sort of subscribed to this Terry Pratchett thing, which also became a thing on the internet when he died, that a man is not dead while his name is still spoken. And as some of you may know about Terry Pratchett, there's this one of his books has basically the internet. It's this semaphore clacks towers that send messages through. It's a fantasy setting, right? And they have this thing where if one of the operators of the internet dies, their name will keep being transmitted through it. And when Terry Pratchett died, it became a thing that you can put his name into HTTP headers and email headers and so on. And he is kept alive across the internet. And I think this is a really nice way of remembering someone who's not with us anymore. And I'm hoping to do the same with Dave by talking about him here, talking about his work. And I will end with a couple of sort of higher level principles that was something that Dave was very focused on, and that I think is valuable for us all to remember the way we work with things. One of them is this concept of open and repeatable research, not just reproducible, but repeatable. So his idea is that yes, you can write a study that you can technically replicate, like is the traditional in science. But especially with computers, things are so complicated that you might not be able to to actually reconstruct the setting that there was. You don't have the time to reproduce it. You may not, if you write a paper, you may not be able to actually go from the description in the paper back to what was the experiment. This is a slide, by the way, from a talk that Dave gave at the SIGCOMM conference in 2014, I think, trying to get the world of academia to to do things the way that the open source world do, by making sure that the code is there. So we should be able to repeat the experiment, not just reproduce it, which means share the code, share your setup, share scripts, make sure everything is there, so someone else can come and rerun the experiment exactly the way it is, because that is how they will find all the bugs. There will be bugs in your experimental data, especially when you publish academic research, but in general, getting more eyes, and we all know it from open source development, right? With enough eyes, all bugs are shallow, but we need to be able to actually get eyes on it, as like things like Heartbleed showed us. So doing the extra work of making everything repeatable, put things in a GitHub repository, let others try it out. That is the way that we can actually get to real insights, get to new things that keep working, and get things upstream is the equivalent also for Linux. Get more eyes on it, get more people to look at your stuff. And the other thing is a relentless focus on latency. So in networking, you usually, a lot of benchmarks will be all about bandwidth, see how fast we can go. We can send gigabits and gigabits of data, but to do so, we increase the buffer size to the maximum we could, and the latency will be terrible. So this is a nice quote of Dave's from a paper that's linked there. Every moment of our lives is precious, and every moment spent waiting on a computer is wasted. We optimize our lives almost subconsciously in a quest for lower latency between what we want and how fast we get it. In improving mankind's interpersonal latency, I'd like us to always aim at the speed of light and ever closer to the speed of thought. So take this principle with you when you design your applications, your protocols, your networking, everything. Always focus on the latency, because that is the delay that we as humans have to wait on. We shouldn't be waiting on the computers. They should be ready when we are to use them. Some further reading and another Terry Pratchett quote. Thank you. Yes.
So you said that all the
Shall I catch box? This one? Try now. I pressed something here. Try now. No? I can press more buttons.
all Wi-Fi drivers implement AQN, but I remember Valu was here a few years ago, and he said that actually most researchers use ATH9K because there's less firmware on that.
Yes.
Is there any? I know from certain CPU trick that the more you implement in firmware, the harder it is to control. So, is all the nice features that they have implemented in all the Wi-Fi drivers, or are there like ATH10K, ATH11K? Do they have all the nice features?
Yeah, no, unfortunately not. No. So a lot of newer hardware chips. So Ath9K is 802.11n, which is ancient now, and a lot of the newer chips move more stuff to firmware, which limits what we can do. And Ath10K is really firmware heavy, and the firmware is not very good. I think Ath9K, Ath11 and Ath12K is similar, moving more stuff to firmware. The MediaTek chipsets NT76 and 79 have less firmware, and MediaTek pays Felix Fiedkow to implement their upstream driver, who's also the original author of Ath9K. So that is, in my opinion, the best sort of hardware in terms of all these features to get these days. But unfortunately, it's...
Do you have some example of what are the features that you can?
Yeah, so airtime fairness, the scheduling where you can, where you try to even out slow stations and fast stations, is not in Ath10K and 11K, I think. But the MediaTek drivers have it, and also some drivers implement in the driver the intermediate queuing, and some use a compatibility layer which doesn't work as well, and also some firmware will queue up packets, so you have this problem where you will end up queuing too much in the firmware. You have so Ath10K has this AQL, the queue limit thing, which helps with that. I'm not sure if Ath 11K and Ath 12K actually have this as well. So there's been sort of progress, but it's a bit uneven between the drivers, unfortunately. Nice. Thank you. Yes. Yeah, so the question is, how do you make sure your research is repeatable as an academic? And I would say the primary thing is to share code and share details. So depending on what you're doing, right? Some things you can package up in a nice run this file and we'll run the experiment if you're doing simulations or if you're doing something that's virtual. If you're doing tests on real hardware, it's harder. You can still share scripts and set up stuff and everything, and then make sure you share all details about hardware versions, firmware versions, chips, all this stuff, so that someone can go out and replicate it. And even if they can't get the same hardware, they can sort of see, okay, maybe the difference is because the hardware is different, and then it in itself is valuable. But it's also like I experienced this myself as a PhD student. Like, you get something and you spend a lot of time figuring out weird things that are going wrong. That's not actually what you want to look at, but sort of tweaking your setup environment, and you have some very bespoke scripts that work in your environment, and then you're done, right? Because then you publish the paper and then you move on. But actually, I think also in academia, a lot of conferences and publications have started actually paying attention to this and saying reproducible batches and all this stuff. But I think, to me, the gold standard is have a GitHub repository with your code that people can look at and run, and make sure that it's documented in a way that you can set it up and run it. There's also this repository where you can share artifacts and it gets a DOI. I forget what it's called right now, where you can actually upload all your data, even like many gigabytes of it, and it will be and sort of get this immutable DOI that you can put into your paper and reference, and it will be around, so your data doesn't disappear. And like, I have terabytes of test results from my own experiments as a PhD student that I'm still hosting myself, because this was before that.
Dave was very test-driven.
Yeah.
So if you did something that he didn't test, he would test it several times after.
Yeah.
So.
And like, asking also, you can also do things like if you're working in a space like I was with Wi-Fi, that was the OpenWRT community, and you can go on, like if you package things up so that it's runnable, you can actually get the community to test it and get feedback and run it in real world situations. And the real world is really annoying, so you will get a lot of weird failure modes that you will not get otherwise. All right. Thank you very much.